An audio track collected during Jupiter mission's Ganymede flyby offers a dramatic ride-along. It is one of the highlights mission scientists shared in a briefing at American Geophysical Union fall meeting. Sounds from a Ganymede flyby, magnetic fields, and remarkable comparisons between Jupiter and Earth's oceans and atmospheres were discussed during a briefing today on NASA's Juno mission to Jupiter at the American Geophysical Union fall meeting in New Orleans. Juno Principal Investigator Scott Bolton of the Southwest Research Institute in San Antonio has debuted a 50-second audio track generated from data collected during the mission's close flyby of the Jovian moon Ganymede on June 7, 2021. Juno's Waves instrument, which tunes into electric and magnetic radio waves produced in Jupiter's magnetosphere, collected the data on those emissions. Their frequency was then shifted into the audio range to make the audio track. This soundtrack is just wild enough to make you feel as if you were riding along as Juno sails past Ganymede for the first time in more than 2 decades, said Bolton. If you listen closely, you can hear the abrupt change to higher frequencies around the midpoint of the recording, which represents entry into a different region in Ganymede's magnetosphere. Radio emissions collected during Juno's June 7, 2021, flyby of Jupiter's moon Ganymede are presented here, both visually and in sound. Credit, NASA/JPL-Caltech/SWRH/University of Iowa. Detailed analysis and modeling of the waves data are ongoing. It is possible the change in the frequency shortly after closest approach is due to passing from the night side to the day side of Ganymede, said William Kurth of the University of Iowa in Iowa City, lead co-investigator for the waves investigation. At the time of Juno's closest approach to Ganymede, during the mission's 34th trip around Jupiter, the spacecraft was within 645 miles, 1,038 kilometers, of the Moon's surface and traveling at a relative velocity of 41,600 miles per hour, 67,000 kilometers per hour. Magnetic Jupiter. Jack Connerny from NASA's Goddard Space Flight Center in Greenbelt, Maryland, is the lead investigator with Juno's magnetometer and is the mission's deputy principal investigator. His team has produced the most detailed map ever obtained of Jupiter's magnetic field. Compiled from data collected from 32 orbits during Juno's prime mission, the map provides new insights into the gas giant's mysterious Great Blue Spot, a magnetic anomaly at the planet's equator. Juno data indicates that a change in the gas giant's magnetic field has occurred during the spacecraft's 5 years in orbit, and that the Great Blue Spot is drifting eastward at a speed of about 2 inches, 4 centimeters, per second relative to the rest of Jupiter's interior, lapping the planet in about 350 years. In contrast, the Great Red Spot, the long-lived atmospheric anticyclone just south of Jupiter's equator, is drifting westward at a relatively rapid clip, circling the planet in about 4.5 years. In addition, the new map shows that Jupiter's zonal winds, jet streams that run east to west and west to east, giving Jupiter's its distinctive banded appearance, are pulling the Great Blue Spot apart. This means that the zonal winds measured on the surface of the planet reach deep into the planet's interior. The new magnetic field map also allows Juno scientists to make comparisons with Earth's magnetic field. The data suggests to the team that dynamo action, the mechanism by which a celestial body generates a magnetic field, in Jupiter's interior occurs in metallic hydrogen, beneath a layer expressing helium rain. Data Juno collects during its extended mission may further unravel the mysteries of the dynamo effect not only at Jupiter, but those of other planets, including Earth. Earth's oceans, Jupiter's atmosphere. Leah Siegelman, a physical oceanographer and postdoctoral fellow at Scripps Institution of Oceanography at the University of California, San Diego, decided to study the dynamics of Jupiter's atmosphere after noticing that the cyclones at Jupiter's pole appear to share similarities with ocean vortices she studied during her time as a doctoral student. When I saw the richness of the turbulence around the Jovian cyclones, with all the filaments and smaller eddies, it reminded me of the turbulence you see in the ocean around eddies, said Siegelman. These are especially evident in high-resolution satellite images of vortices in Earth's oceans that are revealed by plankton blooms that act as tracers of the flow. The simplified model of Jupiter's pole shows that geometric patterns of vortices, like those observed on Jupiter, spontaneously emerge and survive forever. This means that the basic geometrical configuration of the planet allows these intriguing structures to form. Although Jupiter's energy system is on a scale much larger than Earth's, understanding the dynamics of the Jovian atmosphere could help us understand the physical mechanisms at play on our own planet. Arming Perseus. The Juno team has also released its latest image of Jupiter's faint dust ring, taken from inside the ring looking out by the spacecraft's Stellar Reference Unit navigation camera. The brightest of the thin bands and neighboring dark regions seen in the image are linked to dust generated by two of Jupiter's small moons, Metis and Adrastea. The image also captures the arm of the constellation Perseus. It is breathtaking that we can gaze at these familiar constellations from a spacecraft a 500 million miles away, said Heidi Becker, lead co-investigator of Juno's Stellar Reference Unit instrument at NASA's Jet Propulsion Laboratory in Pasadena. But everything looks pretty much the same as when we appreciate them from our backyards here on Earth. It's an awe-inspiring reminder of how small we are and how much there is left to explore. Juno Waves. The WAVES instrument measures radio and plasma waves in Jupiter's magnetosphere, helping us understand the interactions between the planet's magnetic field, atmosphere, and magnetosphere. WAVES also pays particular attention to activity associated with auroras. Jupiter's magnetosphere, an enormous bubble created by the planet's magnetic field, traps plasma, an electrically charged gas. Activity within this plasma, which fills the magnetosphere, triggers waves that only an instrument like WAVES can detect. Because plasma conducts electricity, it behaves like a giant circuit, connecting one region with another. Activity on one end of the magnetosphere can therefore be felt somewhere else, allowing Juno to monitor processes occurring in this entire, giant region of space around Jupiter. Radio and plasma waves move through the space around all of the giant, outer planets, and previous missions have been equipped with similar instruments. Juno's WAVES instrument consists of two sensors. One detects the electric component of radio and plasma waves, while the other is sensitive to just the magnetic component of plasma waves. The first sensor, called an electric dipole antenna, is a V-shaped antenna, 4 meters from tip to tip, similar to the rabbit ear antennas that were once common on TVs. The magnetic antenna, called a magnetic search coil, consists of a coil of fine wire wrapped 10,000 times around a 6-inch long, 15-centimeter, core. The search coil measures magnetic fluctuations in the audio frequency range. More about the mission. JPL, a division of Caltech in Pasadena, California, manages the Juno mission for the principal investigator, Scott J. Bolton, of the Southwest Research Institute in San Antonio. Juno is part of NASA's New Frontiers program, which is managed at NASA's Marshall Space Flight Center in Huntsville, Alabama, for the agency's Science Mission Directorate in Washington. Lockheed Martin Space in Denver built and operates the spacecraft.